Hello students, welcome to my channel. In this video, I am going to explain chapter real numbers of 10th class. What is a real number? Already I started your analysis on real numbers. Yes. So the definition of real number is any number that can be plotted on the number line is called a real number. So we plot the numbers which are plotted on the number line to the right of 0 are positive numbers. The numbers which are plotted on the number line to the left of 0 are the negative numbers. So any number that can be plotted on the number line is called a real number. That line is called a real number line. So you know about all these numbers. Yes. So these are the natural numbers, set of natural numbers denoted by the letter n. These are the whole numbers. Natural numbers along with 0 are called the whole numbers, set of whole numbers denoted by the letter w. Whole numbers along with negative numbers are called the integers, set of integers denoted by the letter z or I. The numbers which can be written in p by q form, where pq belongs to z and q is not equal to 0. These type of numbers are called the rational numbers. The set of rational numbers denoted by the letter q. The numbers which cannot be written in p by q form, where pq belongs to z, are called the irrational numbers. So the set of irrational numbers denoted by the letter s. So there is another definition of the real numbers, that is combination of rational numbers and irrational numbers are called real numbers. So definition of the real numbers is the collection of all rational numbers and irrational numbers is called real numbers. Here it is the definition of rational number. A number which can be written in p by q form, where pq belongs to z and q is not equal to 0, is called a rational number. A number which cannot be written in p by q form for any integers p and q is called an irrational number. So the combination of these two numbers is called a real numbers. So the set of real numbers denoted by the letter R, set of rational numbers denoted by the letter Q, set of irrational numbers denoted by the letter Q dash or S. So what is the decimal expansions of the rational numbers and irrational numbers? What about? So the decimal expansions of rational numbers is either terminating decimals or non-terminating recurring decimals. In terminating decimals, the number stops at a point. It terminates. So 1 by 5 value is 0.2. 9 by 4 is 2.25. So the number stops at a point in terminating decimals. But in non-terminating recurring decimals, the number do not stop. It repeats infinitely. Here 1 by 3 value is 0.3333, so on. So here after decimal point, the digit 3 is repeating infinitely. In the second one, after decimal point, the digits 3 and 6 are repeating infinitely. So first, in these first two examples are the these type of decimals are called the pure repeating decimals. But in the third one, after decimal point, 2 is not repeating, only 6 is repeating. These type of decimals are called the mixed repeating decimals. Next, coming to the decimal expansions of the irrational numbers, it is non-terminating, non-recurring decimals. In it, the decimals of the digits after decimal point do not end, and there is no specific pattern in the reoccurrence. So these type of decimals are called the non-terminating, non-recurring decimals. So let us continue our discussion on the real numbers. In this chapter, you are going to know more about the important properties of the integers. Those are Euclids division lemma, Euclids division algorithm, fundamental theorem of arithmetic, and another new topic, logarithms. First, let us know about the Euclids division lemma. It tells about divisibility of integers and stepwise procedure to compute the HCF of two numbers. So the stepwise procedure is known as the Euclids division algorithm. So the theorem of the Euclids division lemma is, given positive integers a and b, and there exists unique pair of integers q and r satisfying a equal to b into q plus r, where 0 less than or equal to or less than b. Here it states that any positive integer a, any positive integer a can be divided by another positive integer b in such a way that it leaves the remainder r. That is here. A is dividing by b. It leaves the remainder r. That is, it is equal to 0 or less than b. So here quotient is q. So for example, 50 and 70 are the two positive integers. When 70 is divided by 50, it leaves the remainder 20. It is less than the divisor. 20 is less than 50. So this lemma is nothing but a restatement of the long division process. That is, dividend equal to divisor into quotient plus remainder. So the dividend a equal to divisor b into q, the quotient, plus remainder r. So it is the theorem of the Euclids division lemma. The application of the Euclids division lemma. So using Euclids division lemma to show that any odd positive integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5, where q is some integer. So what we have to prove? Any odd positive integer is of the form 6q plus 1 or 6q plus 3 or 6q plus 5. So what are the odd positive integers? 1, 3, 5, 7, 9, 11, 13, 15. These are so on. These are the odd positive integers. When these odd positive integers are divided by the 6, what are the remainders? Remainders are 1, 3, 5, 1, 3, 5. So remainders are 1, 3, 5. When odd positive integers are divided by 3. So that is we have to prove. Without calculating it using Euclid's division lemma, we have to prove that. So let us consider A is any odd positive integer and B is 6. So what is Euclid's division lemma? That is, let any two positive integers A and B, and there exist q, the integers q and r satisfying A equal to bq plus r, 0 less than or equal to r less than b. So comparing with it, A equal to b is 6, 6q plus r, where 0 less than or equal to r less than 6. So what are the values of r? 0, 1, 2, 3, 4, 5. If these values are substituting in it, so if r equal to 0, A equal to 6q. When r equal to 1, A equal to 6q plus 1. When r equal to 2, A equal to 6q plus 2. When r equal to 3, A equal to 6q plus 3. When r equal to 4, A equal to 6q plus 4. When r equal to 5, A equal to 6q plus 5. So in this, 6q plus 2, 6q plus 4. In these three, the remainders are 0, 2, and 4. So those numbers are divisible by 2. So those are the positive integers. 6q plus 2, 6q plus 4 are the even positive integers. So the remaining 3 are the odd positive integers. So any odd positive integers is of the form 6q plus 1 or 6q plus 3 or 6q plus 5. So we proved that any odd positive integer is of this form. Next example is about using Euclid's division algorithm, how to find the HCF of the two given numbers. What is the algorithm? What is Euclid's division algorithm? Algorithm means a series of well-defined steps which provide a procedure of calculation repeated successively on the results of the earlier steps till the desired result is obtained. So that is the algorithm. So using algorithm to how to compute the HCF of the two numbers, two positive integers. Here 1651 and 2032. The two numbers are given. In it, 2032 is greater than 1651. When it is divided by 1651, the remainder is 381. Quotient is 1. Using Euclid's division lemma, we can write it as the dividend A equal to B into Q plus R. That is 2032 equal to 1651 into the quotient 1 plus the remainder 381. So, but the remainder is not equal to 0. So we have to apply the Euclid's division lemma to the divisor and the remainder till we get the remainder as 0. So next divisor considered as the dividend and a remainder considered as the divisor. After dividing it by 381, the remainder is 127. Here also the remainder is not equal to 0. So again apply the Euclid's division lemma. 381 considered as dividend and 127 considered as the divisor. Here also the remainder, when 381 is divided by the 127, the remainder is 127. Quotient is 2. Here also the remainder is not equal to 0. So again apply the Euclid's division lemma. 127 as the dividend. Here the remainder 127 as the divisor. So here after dividing it by 127, the remainder is 0. So here we got the remainder as 0. So the HCF of these two numbers is 127. So it is the how to finding the HCF of two positive numbers using Euclid's division algorithm. In the next video, I will explain the fundamental theorem of arithmetic.